Good morning and welcome again. Last class में we were discussing about autochthonous sediment. We have discussed about limestone and dolomite, in which condition they form, what are the modes of their origin, and what and how diagenetic process work in carbonate rocks, how it affect the porosity. Today we will discuss another type of autochthonous sediment. We will be studying about evaporite minerals. As we have read earlier, in evaporites we are going to see anhydrides, halite and potash salt. Okay, now how these evaporites form? They form largely by the precipitation or crystallization of salts at the sediment water interface. Means at the sediment water interface at the bottom of the sea you are going to see evaporite. At that place they get crystallized, or you can say precipitate. Okay. Another term is brine. What are brines? Brines are the saline rich fluids, means the water which has high salinity. Okay, and these brines are responsible for the formation of evaporites. And now how these brines, evaporates, are going to form? They are formed by the evaporation or freezing, or as residual connate fluids in the subsurface. Say suppose you have 1 liter of water and you have 100 grams of salt in it. Okay, now the water is saline but not the brine. They are not enough to precipitate salt. Okay, so what you are going to do, so you will heat the solution. Okay, now after heating you see that most of the waters got evaporated and the residual water which has high concentration of salt. Okay, now what has happened? Volume of water has decreased but the volume of salt remains the same in it. So the water became saltier and saltier with increase in evaporation. Okay, now at one instance you will see that the salt get precipitate, or only the salt left as residue. Okay, now the another thing is freezing. So similar things, when you have 1 liter of water and 100 grams of salt in it, and you put it in freeze. Okay, so you will see the fresh water. Okay, the fresh water get freeze and the residual liquid which will have this high concentration of salt. Okay, so these are the two things in which you see uh, or form the brines, and these brines ultimately leads to the formation of evaporite. And one more another process is as residual connate fluids in the subsurface. Connate fluids, you know, the water which is trapped in sedimentary layer, that is known as connate fluid, and this residual connate fluid can also responsible for the formation of evaporites. Now these are the process in which you will find evaporites. Now discuss about the secondary brines. Now these brines can form when meteoric groundwater passes through the dissolved previously formed evaporites. So now you have evaporites. Okay, you have brines, and brines get ultimately precipitate brines ultimately precipitate the salt, and now you have evaporites. Okay, now from somewhere you will see that meteoric water, okay, the meteoric water come in contact with that evaporites, and evaporites are easily soluble in water, so it again became that fluids, okay, that meteoric water saline. Okay, and now the same process will happen, and this saltier water gets slowly converted into brines by the process of evaporation or freezing, and ultimately leads to the formation of evaporite. So these are the secondary methods for the formation of evaporites. Once you have evaporite formed, and again it get dissolved in the water, and again it form evaporite. So these are the secondary process in which you will see evaporites get formed. Now the normal ocean water contain 3.45% by weight of dissolved substance. Okay, now you will see that if you have 1 kg of water, you will see 3.45% of the constituents are dissolved, and 99.99% of the dissolved matter comprises of the 9 ions. Means the 99% of them are the major 12 ions. Which are the major 12 ions? That is sodium, magnesium, calcium, potassium, strontium, chloride, sulfate, bicarbonate and bromine. These are the 12 most prominent ions you will see in the seawater. So what is the concept here? That if you have 100 liters of water, you will get 3.45 liters. 3.45 liters you will get in dissolved state, and in that 3.45 liters you will find that these 12 ions are contributing to 99.9% of the dissolved material. Okay, now you will see one figure, some of the common examples, common evaporite minerals. So generally anhydrite, gypsum, polyhalite, epsonite, and these are the common evaporite minerals. You need to know which are sulfates and which are chlorides and what are their chemical composition. Silvite is very common, that is potassium chloride, that is KCl. Okay, remember the compositions, and they are sulfides or they are they are sulfates or they are chlorides. What are they? Actually these need to remember. Okay, now come to the next page. Now a particular attention was paid to volume and composition of the mineral which formed at particular temperature and phases of evaporation. Means you have now different types of evaporites, and these evaporites forms at different temperature and need different volume and composition for their precipitation. So now these studies demonstrate the two main facts. What are the two main facts? That inconceivable quantity of seawater were necessary to form observed volume of evaporites in a closed system. Means if you want to precipitate evaporite or you want to form evaporite, no one knows how much water is necessary for the formation. Okay, so there is inconceivable quantity of seawater. Means there is unimaginable quantity of water you need for the precipitation of evaporite in a closed systems. So one of the fact is that. Okay, now the another one is that the percentage of salt you see in an evaporite assemblages, that is completely different from those that are precipitated by the evaporation of seawater. Okay, now what are the two main facts that have been demonstrated? That a inconceivable quantity means an unimaginable quantity of water you are going to need for the formation of evaporite in a closed system. So this is the one fact. And another one is that the percentage of salt you see in evaporite assemblages, that is completely different from that which has precipitated by the process of evaporation of seawater. Okay, so to amplify the first of these points, means which point? An unconceivable quantity of water, that point, that a column of seawater which is 1000 meter high, means 1 kilometer high, would evaporate out to form 14.85 meter of salts. Means if you have 1 kilometer thick column of water, you are going to get only 14.85 meter of salt from that. Okay, This is important. Many evaporites basin, however, are thousands of meter thick and thus simplistically requires improbably large volumes of seawater to beget them. So now when you see, you get a 1,000 meter thick evaporite basin. Okay, so you can imagine how much water was previously there. So this 100 kilometer, I mean thousands of meter, okay, thick evaporite basin you get. Okay, so 1 kilometer high means thick basin will expelled only 14.85 meter of salt, and now you are getting on the earth surface a thousands of meter thick column. So you can imagine how much thick water column was previously there. Okay, now the next point is the incipient brine sinks to the basin floor because of its high density. Okay, you know that saline water has high density compared to the fresh water. So the saline water, as it gets more saltier and saltier, this saline water gets slowly gets a high density, its density get increased and they starts to sink. The sill prevent drainage of the brine out to the open ocean. So what is sill? Sill, you know, horizontal. You have learnt in igneous, you have sills and dikes. Dikes are the vertical migration of magma and the sills are the horizontal migration. So here the high density saline water work or act as a sill. Okay, so these sills prevents drainage to the brine out to the open ocean. So these sills hinder the drainage or the movement of seawater to the open ocean. Okay, now continuously recycling of the brines increase concentration to the point at which evaporites begin to crystallize on the basin floor. So this is the same process I have taught you earlier. So see, now you have a basin, a sedimentary, a seawater which is saline, as we all know. So gradually you will see that the water gets saltier and saltier and it's start to sink. So at an instant when the water, saline water, became high denser, or you can say their salinity increase at a point where now no solubility can happen. Okay, so at that instant, at that point, these evaporite get crystallized at the bottom of a sea floor. So here at the bottom you will see a diagram. Okay, I mean figure. So you see that limestone to potassium halide, there is a increase in salinity. Okay, so dolomite and limestone, you are going to see that they get precipitated in normal seawater, whereas anhydrite, rock salt and potassium, you need brines. Okay, you means more saltier water. Okay, so the salinity increases from the limestone to potassium salt, which is carnallite, polyhalite, etc. Okay, so this is the thing. So these evaporite also describe the condition in which they have formed. If you form potassium salt, you can tell that they have formed in the brine environment. Means they the water that is needed for their formation have high salinity, and if you form limestone, you can tell that they have formed in normal seawater. Okay, not that much salinity is needed. Okay, now again see the classification of marine evaporite on the basis of mineral composition. You will see chloride, sulfates and carbonates. Okay, so you have different mineral names, that is halite, sylvite or carnallite, that they come in the chlorides group, and the langbeinite, polyhalite, kainite and anhydrite, gypsum, caesarite, and these comes in the sulfates, and the calcite, magnesite and dolomite, you all know that they come in carbonate. The formula is important. Okay, and the rock name. Okay, this is a chloride. Okay, the rock found from the chlorides in which halite minerals are abundant, you are going to say that these are halite or rock salt. Okay, and see the potash salt. Okay, the rock name is potash salt. They comes in both groups, that is chlorides and sulfates. Okay, both mineral class you will see the potash salt. And the anhydrite, gypsum and kieserite, you know, all know that, and that is anhydrite. And gypsum carbonate, you all know limestone and dolomite. So this is not that much important, but you need to know their names or in the mineral class in which they occur, and the what are the chemical compositions. Okay, so now an important term, that is chicken wire structure. So when you heard about the chicken wire structure, so these are generally found in anhydrite. Okay, so these are the term used for the particular type of mosaic or nodular anhydrite. Okay, so if you found an anhydrite which is like mosaic or nodular, so you will say that this anhydrite comprises of chicken wire structure. So one thing is important, that someone can ask you, or in exam you will get chicken wire structure you will find in, so the answer is anhydrite. Okay, now you will see the least soluble compounds are precipitated first. Okay, so what that does that means, that least soluble means that don't get easily soluble will precipitate first. Okay, so the calcium carbonate is the first precipitated out of the seawater. Okay, so they are the least soluble. Okay, so these can't continue to get dissolved in seawater at every at every salinity or every temperature pressure condition. So these are the least soluble, they get precipitated first. They can't bear all the types of conditions in which the water exists. Okay, so these are the first to precipitate out of the seawater, which is followed by the calcium sulfate and sodium chloride. Okay, now potassium sylvite. Sylvite is KCl. So and these magnesium chloride will only precipitate once seawater has become very concentrated. Okay, so this also is the sequence of precipitation in which you will see the calcium carbonate get precipitated first, and then calcium sulfate. You need to remember them which will precipitate first and which will precipitate then after. Okay, so the calcium precipitated first, and then you will see calcium sulfate, and then sodium chloride, and then potash salts, and then magnesium salt. Okay, magnesium salts are last, okay, to get precipitated. They are the last because they get dissolved, they get in dissolved state at various range of conditions. Okay, that is temperature, pressure, salinity, so they get easily dissolved. Okay, so these are the last to get precipitated. Which one? The magnesium chloride. So you need to remember the sequence of precipitation. Someone can ask you in the exam. Okay, this we have completed our evaporites, nothing more important in them. Okay, now we will come to sedimentary phosphate. Okay, so the calcium phosphate occur in igneous rock as the mineral apatite. Okay, so if someone asks you which phosphate, a phosphate rock in igneous, so that you need to say the apatite. Apatite is the only mineral in igneous rock which has phosphate content. Okay, so this is very much important, remember that, which is a common necessary mineral in many granitic rock, and you will see in granites. Okay, some apatites is preserved in sediment as mineral grains, so some apatites also get preserved as a mineral grains in sediment. Okay, so these, so what is the main point here, important point here, that apatite is the only phosphate calcium phosphate that occur in igneous rock. Okay, now phosphorus is also common in living organisms. So each living organism has phosphorus content in it. So the phosphatic minerals in the form of bone, teeth and fish scales occur dispersed in many clastic and biogenic sedimentary rocks. So these phosphatic minerals, okay, occur as bones, teeth and fish in many of the organisms. Okay, but high concentrations are uncommon, being found most frequently associated with the shallow marine continental shelf deposit. Okay, now you know that phosphatic minerals are common in the living organism. So this is very rare that they occur at a single point with high concentration. They generally are dispersed. You will see one teeth here, there, one bone there, one something which contain phosphorus are found very far away. So they are not accumulated, or they are not they do not occur in high concentration. Okay, so okay, now being found most frequently associated with the shallow marine continental shelf deposit. So now these sedimentary phosphates are related to the shallow marine continental shelf deposit, and this one is important. Where you will find sedimentary phosphate? You will find them in marine continental shelf deposit. Now the rocks with concentration of phosphate 5 to 25% are called the phosphorite. Now if you found a rock which has the phosphate content of 5% to 25%, so you will call it phosphorite. In some cases the phosphorite is the form of coprolites, which are the fossilized faces of the fish or animals. So the excreta of the fish or animals, okay, so you will get that enriched in phosphate content. So these are also the source for the phosphate. Okay, now the main mode of occurrence of economic phosphate. So you have primary igneous, so that contain apatite, which is about 24% of the world production. So in igneous minerals you only see an apatite as a source for the phosphate, and it contains 24% of the world's production. Okay, now the sedimentary rock, you will see the bedded or placer deposit. Okay, you will see the phosphate in bedded or placer deposit, and that one is which of the minerals occur? That is colofane and apatite. Apatite also occur in sedimentary and apatite also occur in igneous. So first point that you could see that apatite is preserved in the sediment as mineral grains. So these igneous apatite act as a sedimentary placers. Okay, now the sedimentary you see that they occur in bedded and placer forms, which one is colofane and apatite, and they contribute towards 74% of the world's production. And now the another one is guano, that is complex phosphate and nitrates, and that only contain about 2%. Okay, now you know that colofane and apatite are the phosphate content minerals. Okay, so this one is important, and sedimentary phosphates are having the high abundance. Okay, now you have heard about the term guano. Now what guano is? Guano is the guano is a deposit rich in phosphate and nitrates found by the excreta of seabirds and bats. So the birds, bats, okay, so these excreta which are rich in phosphates, when preserved they are known as guano. Okay, so now the modes of formation of phosphate. So there are, okay, so the solubility of phosphate decrease with the increasing temperature and increasing pH. So this one is important. The phosphate solubility, okay, decrease with increasing temperature and pH. When you increase the temperature and the pH, okay, so you will get the decrease in solubility of phosphate. Increase in temperature you understand, but what is increase in pH? Increase in pH means you will move from acid to base. Okay, so the basicity So the increase in basicity will leads to the decrease in solubility of phosphate. Okay, so these changes occur and phosphate thus tend to precipitate where deep cold oceanic water up wells up into the shallow warmer. So you will see the phosphate. Okay, the phosphate deposit where the upwelling took place means the water from the deep below comes out to the surface. At that point you will see a phosphate abundance. Okay, so why you will get phosphate at the upwelling condition? Because what are the condition for the formation of phosphate? That there will be less temperature and less pH. Okay, means the temperature means cool water and high pH. So upwelling waters will have low temperature, is it okay, and they have low pH. So you will see that these forms at the upwelling of seawater. Okay, now the 8 factor favors phosphate formation. So this one is also important. You may get 4 and you may get 3 and 1 wrong and asked to select which of these is wrong. Okay, now the 8 factor favors phosphate formation. A broad shallow shelf. So you need a broad means wide shallow shelf. Okay, shallow shelf, this one is important, and the another one is an adjacent major ocean. Okay, so at the broad shallow shelf you need a adjacent major ocean, and at low latitude means that is less than 40°. Okay, so low latitude region you will see the phosphate where there is a high organic productivity. Okay, now the another one is shallow marine sedimentation. So there should be a shallow marine sedimentation, minimal terrigenous input. So the terrigenous input should also be less, and the marine transgression. Okay, marine transgression means the increase in sea level. Okay, so this one leads to the formation of phosphate, and another one is suitable environmental trap. So they need the region where they get trapped, no sedimentary input, no extraterrigenous input. Okay, such as bay, estuary or carbonate bank. So these type of environment are needed for the formation of phosphate. They need a broad shallow shelf adjacent to them. They need a major ocean. They occur in low latitude region. Okay, thus there must be a shallow marine sedimentation with minimal terrigenous input, and there should be a marine transgression and a suitable environmental trap. Okay, like bay, estuary or carbonate bank. So these are the I mean the process that is important, or the condition that is important for the formation of evaporites. Okay, so with this we have completed our sedimentary phosphate also, and now we will discuss about sedimentary iron ore. Now the iron ore also occur by the process of igneous or as well as sedimentary. So here we will be discussing about the sedimentary process only. Okay, now when you see their mineralogy and in the environment they have formed, so this will help you to know what was the condition at that time they were deposited. And now you will see that there are 4 major groups of sedimentary iron ore. Okay, there are the 4 major groups of sedimentary iron. So the first one you will see that is recent to tertiary, that is laterite, or you can call bog iron ore. So you need to study from the bottom. Okay, the Precambrian. Okay, the very early, the Precambrian, in which we will find the banded iron formation. Okay, these irons are banded. Okay, so now these banded iron formation, they have distributed into 2 parts, and you will see the one is Algoma type and the another one is Lake Superior type. Okay, so the algoma types. Okay, these sedimentary these iron ores have formed in the period of Archean, and they are formed by the submarine volcanism. Okay, so these banded iron forms in Archean age, okay, and by the formation of submarine volcanism. Okay, so these submarine volcanism are responsible for the formation of banded iron banded iron at the Archean. Okay, and these types of banded iron formation is known as algoma type. And the another one is Lake Superior. Okay, these Lake Superior, you will see that they have deposited, okay, they have deposited and form a Lake Superior type of sedimentary iron ore, and they have the age of early Proterozoic. Okay, so Precambrian, you will see the two types of iron ore, that is Algoma and Lake Superior, and their environment, the Algoma formed in submarine volcanism, okay, and the Lake Superior, they are formed by the deposition of the iron ore. Okay, now the another one you will see from Mississippian to Silurian. Okay, now here you will see the Clinton type. Okay, now this Clinton type, and in Jurassic you will see the Minette type. Okay, these names are important, and their age are also. Okay, so the in Jurassic you will see Minette, and in Mississippian you will see the Clinton, and these Minette and Clinton both are of oolite type. Okay, they are spherical shaped, less than 2 millimeter grain size. Okay, so they have the oolitic shape. Okay, which one? The Minette and the Clinton. But the Algoma and Lake Superior, they are banded iron formation. Now from recent to tertiary, nowadays you will see the sedimentary iron, they occur generally as the laterite or as bog iron ore. Okay, what is important? The types of iron ore and in which environment or as well as in which age they have formed. That one is important, you need to remember them. So someone ask you the Minette Clinton, the type of sedimentary deposit, so you need to know that they have oolitic types of deposit. Okay, now the sedimentary iron stones. So the rock with at least 15% of iron are referred to as iron oxide. So if you found a rock which has at least 15% of iron content is there, so you are going to call it iron stones or iron formation. Okay, now in which the iron is in the form of oxide, and here you will see the iron which occurs in the form of oxide, hydroxide, carbonate, sulfides or silicates. Okay, so you only need to know that only 15% is needed to call it as a iron stones. Okay, now we have magnetite, an accessory mineral in igneous rock. Okay, magnetite are the accessory minerals of igneous rock, and detrital grains in sediment. So these magnetite get fragmented or disintegrated and act as a detrital grains in sediment. So these are also a sedimentary iron stones. Okay, now the hematite is the most common oxide. Okay, you all know that hematite is most common oxide, that is bright red to black in color. Okay, they have red or black colors. Okay, and they occur as a weathering or alteration product in a wide variety of sediments and sedimentary rock. So the sedimentary rock, whether their high grade of weathering or alteration leads to the formation of hematite. Okay, now the another one is goethite. Goethite is a iron hydroxide. So this one formula is important, you will see in different exams, you will see the formula of goethite. Okay, goethite is an iron hydroxide, that is FeOH, that is widespread in sediment as yellow brown mineral. Okay, which may be a primary deposit in sediment or is a weathering product of iron rich minerals. So what are goethite? Goethites are the hydroxides, iron hydroxides. They generally occur as widespread in in sedimentary rocks. Okay, and these primary deposit, I mean these deposits are formed by the weathering product of other iron rich minerals. So you have another iron rich minerals and their weathering product leads to the formation of goethite. Okay, now these goethites have the less oxidizing condition than hematite. Okay, so this thing you also need to know that hematite occur in oxidizing condition. Okay, now the next one is limonite. Okay, that limonite is also hydrous. Okay, H2O, that is a hydrated iron oxide. Okay, that they add hydrated iron oxide, that is amorphous. In thin section iron oxides are opaque. So if you see a hydroxide, hydrated iron oxide, okay, sorry, hydrated iron oxide, so you will see you can't see in thin section because they are opaque. Okay, then the next one is pyrite. Okay, this is a common iron rich sulfide minerals, Fe2. Okay, that is pyrite. So these are the common iron sulfide minerals that is found in igneous and metamorphic rock. Okay, so they are these type of rock generally found in igneous and metamorphic rock, and they form a brassy cubical crystals, that is also known as fool's gold. You remember the pyrite is also known as fool's gold. They look like a gold but they aren't. Okay, so these pyrite also act as a sediment. Okay, so also they get disintegrate and act as a okay, sediment. Okay, the next one is glauconite is also known as glaucony. So the glauconite is also a phyllosilicate formed orthogenically in shallow marine environment. So if you see a glauconite, I have taught you about the glauconite and in the environment what are the discussions of their origin. So there are different, so you can go to the back videos, last 2-3 last videos, so go and you can know the differences and in their mode of origin what other scientists are telling and what are and how they form actually. Okay, so glauconite is the phyllosilicate formed orthogenically in shallow marine environment. So if you see a glauconite, you can tell that they have formed in shallow marine environment, and these are also a phyllosilicates. Okay, in clay minerals you will see this glauconite. Okay, last year second last class I have taught about that glauconite. Okay, so anyway, so this now the next one is banded iron formation. Okay, now these banded iron formation, which also known as BIFs, okay, are an example of type of sedimentary rock. Okay, so these occur in banded form. Okay, and these are type of sedimentary rock where there is no equivalent forming to this. So you will not see an equivalent rock to the banded iron formation. Okay, all examples are from the Precambrian. So I have taught you the age of their BIF. They are formed in Archean age. Okay, so you will get the age Precambrian, and most of are from the 2.5 to 1.9. that is 1.9 is a period of oxidation. Okay, so you will get it from them only. Okay, so now the next one is BIF consists of the laminated or thin bedded alteration of hematite rich sediment and other material which are typically siltstone or chert. So banded iron formation, they consist of laminated or thin bedded. Okay, so there is thin or laminated bedded alteration of hematite. It must be there, hematite, and the other minerals which are also associated, these are siltstone or chert. In banded iron formation you will see hematite as layers, and also with that hematite you will see the siltstone or chert. Okay, the next one is they probably formed on widespread shelves or shallow basin. Okay, so they are formed widespread shelves or shallow basin. So the environment they need for their formation is they need widespread shelves and shallow basins for their formation. Okay, now with the iron originating the muddy deposits on the sea floor, possibly in association with the microbial activity. Okay, so what are the condition needed for their formation? That is widespread shelf and shallow basin. They generally originate in muddy deposits or sea floor. Okay, so in sea floor or muddy deposits you will see the banded iron formation. In that condition they only deposit. Okay, and another one is microbial activity is also there. Okay, now the hematite layers. Hematites are the oxygenated water iron precipitate. Okay, so know that hematite occur in oxidized condition. So hematite layer represents that they are oxygenated water, means there the presence of oxygen is there. Okay, that is why the iron precipitates. Now the chert layer you see chert occur in reducing condition in which iron is in dissolved state. So these banded iron formation will describe you the two condition, that one is oxygenated condition in which the iron precipitate and another one is the reducing condition in which the iron dissolve. Okay, so these banded iron formation contain these two conditions. Okay, and in oxygenated water condition, okay, you will see the hematite layer, and in reducing condition you will see the chert layer. Okay, so this one is very much important. You all need to know that these banded iron formation suggest the two periods. Okay, the one is oxygen rich and the another one is oxygen deficient. Okay, so that is why we will not see any equivalent rock nowadays. Okay, now the source of iron is thought to be either hydrothermal or a weathering product. Now from where these iron have came from? So two concepts have been developed, that is they may have come from the hydrothermal vent. Okay, hydrothermal vent you all know, you must know. Okay, the hydrothermal vent or a weathering product. So hydrothermal means you will get a fluid which is rich in iron content, that is coming out from the ocean basin. So that one is hydrothermal basin. Okay, the fluids coming from the ocean floor, okay, that is enriched in iron oxides. Okay, and iron you can tell. Okay, and the another one is weathering of the iron. Okay, weathering means there is existing iron and these irons get dissolved or weathered or eroded. Okay, so in both of these condition the water or the environment get enriched with the iron, and these at suitable condition means what will be the condition? In oxidized condition, these dissolved iron get precipitated at the sea floor. Okay, so and could only have transported at dissolved iron if the ocean waters were not oxygenated. So this is the one of a number of lines of evidence that the atmosphere contained little or no oxygen through much of a Precambrian times. Okay, means now you understand that. So try to understand. Okay, now from the hydrothermal vent, okay, and from the weathering of irons, you will get iron content in dissolved water. Okay, you will get a iron in dissolved form. Okay, now these iron will remain in dissolved condition only when there is a reducing condition. Okay, if there is oxidizing condition, these ions will get precipitated. You all know that for the precipitation of iron you know the oxygenated water. So at that time when the iron from hydrothermal vent or from the weathering comes in solution with the water, at that time the condition was reducing, because if it was not reducing and means oxidizing, the oxygen get precipitated, and at that time they have not precipitated, because the iron that is dissolved in that water need to be transported, okay, transported to a wide area, and then they get precipitated. So what the concept has been evolved, that the time when iron get enriched in seawater, at that time their condition was reducing, and in that period of time the oxygen ions got the time to spread or transport to the wide range, okay. And now at the time when the environment get enriched with the oxygen, means the oxidizing condition, these enriched iron enriched seawater precipitate the iron out of it, okay. And now again after sometimes you will see a chert layer which describes that there were no oxygen at that time. So as a result you will see a chert layer which is overlaid by the hematite layer, okay. So this is the major constituents of our banded iron formation, and these two also describes the formation, describe the environment conditions of high oxygen content and no oxygen content. So this is it. From this we have also completed about the sedimentary irons, and now we all know the important conditions and important thing which is that we need to know and what are going to come in exams. Now the last autochthonous element is the chert. We are going to read about the cherts. So cherts are the hardest sedimentary rock, okay. So chert are the hardest sedimentary rock. And from the last topic of sedimentary iron ore, you know that chert form in the reducing environment, okay. Cherts are the fine-grained siliceous sedimentary rock made up of silt-sized interlocking quartz crystal called microquartz and chalcedony, okay. These are very fine-grained siliceous sedimentary rocks that is made up of interlocking silt-sized quartz crystal, okay, and also of chalcedony. So the chert is a non-clastic sediment composed of microcrystalline quartz. It occur in both conditions. So here is something is missing, so leave it, okay. So the chert is non-clastic sediment, okay. These are not clastic sediment, these are the not clastic sediment, these are non-clastic sediments, and they are the composed of microcrystalline quartz. What is microcrystalline quartz, okay. They have the composition of interlocking quartz crystal. So what is that they occur in both beds and nodules in limestone and sandstone. So you will see the chert as bed and also as nodules, okay, in limestone and sandstone. So you will see the chert as bedded form or as well as the nodules, okay. The four minerals are associated with the chert. Now we will discuss about the four minerals that is associated with the chert. So we have opal or opaline silica, which is amorphous and isotropic, okay. Now the next one is cristobalite, is an isotropic or felted, okay. The next one is chalcedony, is microcrystalline quartz that often shows fibrous or radial habit. And finally we have microquartz, okay. So with anhedral crystal that is of 10 to 50 meter in diameter, I mean millimeter, there must be a millimeter, I have done something wrong, okay. 10 to 50 millimeter in diameter, okay. So we will discuss about the opal, cristobalite, chalcedony and microquartz. Now the beds of chert form either as primary sediment or by the diagenetic process. So the beds of chert, you will see that they are formed by the primary sedimentation or also by the diagenetic process, okay. On the floors of the sea and lakes, the siliceous skeletons of microscopic organisms may accumulate to form a siliceous ooze. Okay, now at the ocean floors or at the lakes, you will see the microscopic organism which has a siliceous skeleton. Their shells get accumulate at the sea bottom and form a siliceous ooze, and this is how the siliceous ooze form. Okay, so now these organisms are diatoms. Okay, so which organism contribute to the formation of siliceous skeleton? So these are diatoms and radiolaria. So they have the siliceous skeleton, so only they are responsible for the formation of siliceous ooze. Okay, so these organisms are diatoms in lakes, and they may also accumulate in marine condition through, although radiolarians are most common, the main component of the marine siliceous ooze. So these diatoms and radiolaria, they have the siliceous skeleton, and these siliceous skeleton get accumulated at the sea bottom to form a siliceous ooze. Okay, now this opaline silica, opal is a cryptocrystalline silica, okay, with water in the mineral structure. So they have water in the mineral structure. So opaline is a cryptocrystalline silica with have a with have water in the mineral structure. Okay, opaline silica of the diatoms and the radiolaria is metastable and recrystallized to chalcedony or microquartz. So these opaline crystals are metastable, okay, and they recrystallize to chalcedony or microquartz. Now we will discuss about the flint. What is flint? That is nodules of chert formed by the replacement of other minerals. So these are the flint. Flint is the nodules of chert, and they are formed by the replacement of other minerals such as calcium carbonate by water with silica. So you have calcium carbonate which is enriched in CaCO3, and they get in contact with the water which is enriched with the silica, and these calcium carbonate are replaced by the silica and form a flint. Okay, now we will discuss about the jasper. Jasper is the hematite causes the strong red color of the jasper. Okay, so jasper is also a type of chert in which you see they impart the red colors, and these red colors is due to the hematite. Okay, hematite have the red color, so it gives the color to the jasper as red. Now we have also black chert. Okay, so the traces of organic material resulting in gray or black chert. So the organic material, so you have chert which is gray, and they have the color of black is due to the organic material. The cherts are found below depth to some 60 meter beneath the modern ocean floors. Okay, so you will see the cherts found at the depth of about 60 meters. Okay, so they occur in calcareous and terrigenous clay. Okay, and in volcanic sediment and in siliceous ooze. So you will see the black chert everywhere, means you will see it in calcareous, terrigenous clay, and also in volcanic sediment, and also in siliceous ooze. Bedded cherts are also known from the lacustrine. Lacustrines means lake. From the deposits of lake you will also see the chert, and in lake you will see the bedded chert, not massive or okay, and fragment shape. Okay, so now their origin. Now we will discuss the origin of chert, how the chert form. So it has been argued that the flint formed some 5 to 10 meter below the sediment water interface, means flint is formed at the 5 to 10 meter below the sea floor. Okay, where porosity was still in the region of 75 to 80%. Okay, about flint, what is the condition? About jasper, what was the condition? About jasper, it is formed 60 meter beneath the ocean floor, and if you discuss about the flint, that they form 5 to 10 meter below the ocean floor, okay, and their porosity still is about 75 to 80%. Anaerobic bacteria sulfate reduction releases H2S. Okay, so the anaerobic bacteria, okay, anaerobic bacteria that is in the uh, oxygen deficient condition, okay, so these bacterial sulfate reduction releases H2S, hydrogen sulfide, okay, and now this reduces the pH and cause the dissolution of chalk and the concomitant precipitation of silica. So what do these anaerobic bacteria do? Anaerobic bacteria sulfate releases H2S, hydrogen sulfide, which ultimately reduce the pH. pH reducing means they are going towards the acidic condition, so reducing the pH, and it causes the dissolution of chalk. You know, the calcium carbonate get dissolved in the acidic condition, so when the pH get decreased, so the chalk, which is also a calcium carbonate, which also has the composition of calcium carbonate, they get dissolves and concomitant precipitation, and at that condition, you know, at the silica get precipitated. At acidic condition you will get silica precipitated, at basic condition you will get calcium carbonate precipitated. So at that condition which have high acidic condition, so here silica precipitate and you will form a sedimentary chert layer, okay. And now in other instant, however, the presence of chert in fracture and of chert replaced carbonate skeleton debris provide conclusive evidence for a secondary origin. So this was the primary origin. What was the primary origin? That the anaerobic bacteria release H2S, which these H2S decreases the pH, and there is the environment of acidic environment. Then there is a condition of acidic environment, and in that these chalk, okay, or chalk you can say, the calcium carbonate get dissolved and the other siliceous element get precipitated and you formed a cherty layer. So this is the primary mode of origin. Now the secondary mode of origin is that there is a presence of chert in fracture. In fracture zones, you will in the fractures of the rock you will see the chert. So how they have reached there? So okay, and now the another one is that the carbonate skeleton is also replaced by the cherty layer. So I have told you earlier that if we have a calcium carbonate rock and a water which is enriched in siliceous content, and these siliceous content get connected in okay, they get connected in what to say, carbonate, in carbonate rock, and these carbonate rock get replaced by the silica rich fluids. So these are the condition for the secondary origin of chert, okay. So now clearly we can say that cherts are polygenetic, okay. They have not one mode of formation, they can form by the many modes, okay. So anaerobic bacteria is also responsible for that secondary chert layer, which is found by the replacement is also there, okay. So these are the process in which chert form, okay. So now with this we have also completed about the chert, the main things I have pointed it out everywhere. So you need to remember what is important and what are the things that you can leave, or you can tell that is not that much important. So with this we have completed about all of the autochthonous sediments. Now nothing is left, we have completed. One coal is left, and now we will not discuss coal in sedimentary here, okay. Everything is completed of autochthonous sediments. Now we will discuss about sedimentary structure. We have to study about sedimentary basins, environment.